Used when all of the initial concentrations are non-zero. If one of the initial concentrations is non-zero, you can usually tell which way equilibrium is going to sway. So, reaction quotient is where we left off last time. Applying the law of mass action, which is basically your K expression. We're going to be using that. We're going to figure out Q using that, and then from there we will be able to tell which way it should go. We're going to substitute, and we're going to check out. Now, you have some possible arrangements for Q versus K, and this is what we're talking about in the write this, not that. When you're talking about Q and K, you would actually need to note in there, if you're calculating initial concentrations, if Q comes out equal to K, showing you right here they're already at equilibrium. And you would state that. You would go Q equals K, so the system reaction is already at equilibrium. Something like that. That's what you would state. We're going to look at the other situations where Q is less than K, if it comes out that way, if Q is greater than K. But if Q is equal to K, the system's already at equilibrium. Not an issue there. That one's the easiest one to remember. And this graphic is really good because it shows you here, too, when Q is less than K up here, like so, in order to reach K, it's going to have to shift. And over here, too, if Q is greater than K, it's going to have to shift in order to get back to equilibrium. That word shift again, proceed towards a certain direction. So, in order to make sure that we're reestablishing the normal proportion that K gave us in the first place. So if Q is greater than K, there's too much product, and so equilibrium shifts to the left to make reactants. So if you would state possibly in your free response, Q is greater than K, there is more product, therefore the reaction will proceed towards the reactants to reestablish equilibrium, something like that. Consuming products forming reactants until equilibrium is achieved. That's another way to say it right there. Another good formal free response way to say that. Now, if Q happens to be less than K, there is going to be too much reactant. So in order to that, you must proceed towards the products, consuming reactants, forming products to attain equilibrium. And if you do think about it, because remember in general, K equals products over reactants, right? So if the Q number happens to be less than K, that means you have a bigger number on your denominator for Q. So that means you have too much reactant going on. And you would want to make product, shift it, proceed to the product side. So if you think about this in generally, this is the law of mass action in general, without the exponents and all that stuff. You can kind of think about how the numbers would work. Q is less than K. You're going to have more reactant than needed initially, and then it's going to proceed towards the products to establish equilibrium. So try and either use the visual aid up here, thinking about it that way with the dotted line, or come up with a system here of being able to tell which way it's going to go. And I believe if you write it as K is greater than Q like that, then it's going to proceed that way. If you write K is less than Q, it's going to proceed this way. So the little way that this arrow is pointing, you can treat it like it's an arrow, but you have to write the K's first if you're going to do it that way. But you can treat the less than, greater than signs as an arrow. Do you see what I'm talking about? That's another way to try to remember. So if you look at this as being an arrow pointing that way, it's going to proceed towards the products. If you look at this as an arrow pointing that way, it'll proceed towards the reactants. But you have to write K first in the, has the alphabetical order, K then Q. So that's another nice, easy system way of remembering. Okay, does everybody see what I'm talking about here? Using it, but K then Q, put the less than or the greater than sign in there. Which way it's pointing will determine which way it's going to proceed. Okay, so I like that. That's a good, easy way of remembering rather than trying to. You could definitely, I like to think about it in terms of just generally products over reactants and thinking about, oh, well, if the Q number is bigger than K, that means it's P on the top must be bigger, so we're going to make some more reactants and so forth. So I like to think of it conceptually as well. Yes? I'm talking about the only way that this one works is if you put K first. K has to be written first, not Q first. So the K here and the K here, the way that the greater than less than signs are actually going to point the direction for you. But K has to be written first, Q has to be written second. So if K is greater than Q, we know that we're going to proceed towards the products. If K is less than Q, we're going to proceed toward the reactants. But that's the only way that we can use these as pretend arrows. If we write Q first, then that system doesn't work. Okay? So that's a helpful way, or if you want to just think about it in terms of generally products over reactants conceptually, that takes a moment to think through, but you'll get the right answer out of it as well. Le Chatelier, my favorite name to say, Le Chatelier. Nice French name. If a system is at equilibrium and is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position as to counteract the effect of the disturbance. This is the formal definition for Le Chatelier's principle. Now, what you basically need to get out of this is if you stress a reaction or a system at equilibrium, it is going to counteract that stress and try to reestablish equilibrium. So that's what we're kind of going for here when we're talking about Le Chatelier. And the factors that can affect equilibrium are going to be temperature, pressure, or concentration. We're going to individually go through them as we talk about Le Chatelier. And then once again, on Thursday, we'll continue to review them and do some more practice problems with Le Chatelier and some more rice chart problems, because we're going to do those as well. So, once again, if you disturb a system or reaction at equilibrium, it is going to have to compensate and change and shift in order to reestablish that equilibrium. And like I said, each individual component, I'm trying to break it down as easily as I could, the way that I remember them, for each individual type of component that can be affected. And there's other little nuances too that they like to throw in to try to confuse you, so we're going to go over those individually as well. Okay? So, the effect of the disturbance, it's a stress. They could also say if they put a stress on the equilibrium system, it's going to counteract that stress, and it's going to either proceed to the other direction in order to reestablish that K value, that proportion of the products over the reactants. So we're going to look at, I believe, concentration first. Let's take a look at how concentration affects. Changes of concentration. The system will proceed to the opposite side from where the component was added. So if you add something to an equilibrium system, it's going to go the other direction. Generally, if a component is removed, say we remove a product, well, it's going to realize that product is now missing, and it's going to try to make more of that product. So if you remove something, it's going to shift to the side that you removed it from in order to replace it. This is also, equilibrium and Le Chatelier principles applied in industry a lot because a lot of reactions do establish an equilibrium, and maybe you want a certain product to be made each time. So if you take it away and remove it from the system, it's going to keep making the product. These kind of concepts are used in, especially that Haber process I talked about. So you need to make ammonia to put in fertilizer. So they're going to remove the ammonia. They're also going to adjust the pressure and the temperature to the right factors to make the most ammonia. So Le Chatelier's principle is definitely applied, in our business and industry to get the most out of our reactants and the most bang for your natural resources here. You want to be able to use it and get, the most product for your cost. So in chemical reactions in chemistry, this is the idea, because a lot of things are reversible, a lot of reactions do establish equilibrium, they're going to apply here. So another way of reestablishing when adding gaseous or aqueous reactants, reactions proceed to the right towards the products. When adding gaseous or aqueous products, reactants proceed to the left towards the reactants. So when you add to the products, it goes the opposite direction. When you add to the reactants, it goes the opposite direction. Remember, too, the only things that can affect a shift or a change in the way it proceeds is going to be something that's gas, something that's aqueous, something that has a concentration. So liquids and solids, you can add them like there's no tomorrow, but it's not going to affect the equilibrium at all. When removing, so if you remove reactants, it's going to shift towards the reactants. If you remove from the products, it's going to shift or proceed towards the products. Yeah, I'm still trying to adjust my way of saying, because I always say shift too. So, looking at this particular example, this is the Haber process, nitrogen plus hydrogen, giving us ammonia. If we add in nitrogen, and I add here, which way is it going to proceed? It's going to proceed towards the right. So in this particular case, we can just draw an arrow. I'm not asking for a sentence-free response or anything from you here. If you add ammonia, so this time we would be adding here, which way is it going to move? Going to shift or proceed towards the reactants. If I remove hydrogen, so in this case I'm going to be removing it, taking it away, it's going to want to make more nitrogen, so it's going to shift or proceed towards the reactants. If I remove hydrogen, it's also going to want to make more hydrogen, so therefore proceed towards the reactants. So this is a very simple Le Chatelier type problem. Effects of changes on the system. For temperature. Now looking at temperature. Temperature is a little bit of a snag because temperature does affect K. So temperature will change your K value, but it also will make you proceed in a certain direction. Adding in heat, because heat really is acting as its own reactant or product in an endo or exothermic reaction. For an endothermic reaction, the heat is acting as a reactant. So it's like adding in an additional reactant that wasn't there before, and it's going to speed up the particles, going to make them move faster, the rates are going to change. So this overall is going to affect your rate and your proportion. That's why K is going to change. In an exothermic reaction, the heat is a product right here, right? Okay? So, it's also, depending upon your reaction, will affect the speed of the particles, which affects the rate of the particles, which affects the collisions, which would also affect the proportions that are going to come out of it. So, the K value will change if you add or take away heat. Now, adding in heat, it depends on which type of reaction you're going to be working with here. Do you know that delta H is positive? So if they tell you a reaction and put delta H positive next to it, you should be able to label it as endothermic. And if they have delta H next to it where it tells you it's a negative value, you should be able to label that as exothermic, so you know where to put the heat in terms of being a reactant or product. So, the system will proceed to the opposite side from where heat is added. So if heat is a reactant because it's endothermic, if you added heat, it's going to proceed to the product, the opposite side. If you have an exothermic reaction though, and you added heat, it's going to go to the opposite side there, and that would be proceeding towards the reactants in that case. So you have to specifically look where the heat is. Is it endo or exothermic before you decide which way it's going to change the equilibrium. Heat is removed, it's going to try to make more of that heat, so it's going to go to the side where the heat is if you remove it. So in an endothermic reaction, if you remove heat, it's going to proceed towards the reactant. If you remove heat from an exothermic reaction, it's going to proceed towards the products. So it's the same kind of concept as concentration. If you add it, it's going to go opposite. If you remove it, it's going to go to that same side. But you got to figure out where the heat is. Is it going to be a reactant or product, depending upon what type of reaction is it? Is it endo or exothermic? Okay? So position that heat in there before you decide which way it's going to move. All right? Same concept, though, as concentration. Adding opposite, removing same. Okay? In terms of which way you're going to proceed. So go ahead and take a look at the next example and see if you can see what's going on there. Heat here has been labeled for you as part of the reaction. What type of reaction is this? This is going to be endo. Delta H is going to be positive. Like some things like that you can tell. So if I increase the temperature, I'm really adding in heat. So which way would it move? Which way would it proceed? In this case, we're increasing temperature. It's going to proceed towards the products. If we decrease the temperature, it's going to proceed towards the reactants, because we're removing heat now, taking it away, it's going to want to make more of that heat. Now let's look at the overall effect of K. If you increase the temperature here, what are we making more of? This is where you go to that generalized equation. Increasing the temperature makes more of the what? So the product number increases, the reactant number is going to decrease. So what happens to our K value? K is going to increase here. K is going to get bigger, because your product number will get bigger on top, your reactant number will get smaller on the bottom, so K ultimately is going to increase. So the opposite is true here. If K is products over reactants in general, and we are making more reactants, this is going up, your products are going to be decreasing. So generally, K is going to decrease. Okay, does that make sense? Thinking about the way it's going to move the K value? Yes? If it was exothermic, pretty much yes, but you would want to approach it from conceptually looking at it. If I have an exothermic reaction, I'm increasing the heat, it's going to make more reactant, so the K would decrease in that case, yes. Okay? This is the only time where K would ever change, though. So for pressure, for concentration, K stays the same. It just keeps going back and forth until it reestablishes that proportion that was originally there. But remember, heat does affect the speed and the collisions and all that other stuff, so it does affect the proportions of the concentrations that you ultimately will end with, because you have kinetics involved in here. All right, pressure. There's lots of things to look at pressure. First thing you need to look at is the number of moles of the gas, because the only thing that's going to exert a pressure is going to be what? That gas. So you need to look at the number of moles of the gas first. That's important. And decide how many moles of gas you have on your reactant side, how many moles of gas do you have on your product side. So decide that first before you even look at which way it's going to proceed. Increasing the pressure is going to make you proceed to the side with the least number of moles. Decreasing the pressure is going to have you proceed to the side with the higher number of gaseous moles. So, the other thing that they like to throw in for AP, they like to word it using volumes, increasing and decreasing volumes. So this is where they wedge in some of that gas law stuff for you. Because who is the guy that talked about the relationship between pressure and volume? That's Boyle's, right? Boyle's law. So if you increase the volume, what happens to the pressure? Pressure goes down, right? Because it's the one that's inverse here. Pressure goes down if volume goes up, according to Boyle's law. And if the volume decreases, then the pressure increases. Because remember, this is the inverse relationship here. So we have this inverse relationship. So if pressure is increased, that means the volume would decrease. So they might say the volume is decreased. So then you have to go, oh, the pressure is increasing. I need to go to the side with the least number of moles of gas. You need to have it proceed that direction. Another little tidbit they throw in here under pressure is they tell you they're going to insert an inert gas. And the inert gases are going to be your noble gases because they're the non-reactive gases. So, are the non-reactive gases going to play any role in our reaction? They're not going to actually react with anything in the vessel, right? So, it's not going to change the pressure of the equilibrium system. All it does, generally, if you add in some noble gas, is increase the overall pressure of the system. It doesn't actually change the individual reactant or product amounts based off of the pressure. And remember, pressure is exerted by the gaseous molecules hitting the walls of the container, and it wants to maintain that same pressure system. So, if the pressure increases, it's going to adjust it so that you get less moles of particles, so then you have less things hitting the wall, so the pressure goes back to its original state that it was at before you put the stress on the system. Same thing occurs there. If you take away pressure, it thinks it should be at this number, so it's going to create more moles of gas to hit the walls of the container and reestablish that pressure that it was originally at. Okay? So there are lots of things that can change and go in the way they can word the pressure questions here. So make sure, don't be fooled by the inert gas one, because that doesn't do anything to equilibrium. It just adds overall pressure to the system. And make sure you realize and go back to Boyle's law, realizing that you increase or decrease the volume, that ultimately is affecting the pressure. So you need to, reframe it that way. Okay? Let's take a look at our example here. So pressure, must look at the number of moles. So the first thing I do if I'm given a pressure question is I go, oh, there's 1 mole plus 3 moles. So this side is going to have 4. Over here I have 2. So I have 4 moles to 2 moles, looking at my reaction above here. So if I increase the pressure, which way am I going to proceed? Right. Towards the right. Here we're going to increase pressure, and we're going to go to the side with the least number of moles, which happens to be towards the ammonia there. Only 2 moles, 4 to 2 here. If I decrease the volume, what's going on here? Decreasing the volume means I'm increasing pressure, so once again going to the side that has the least number of moles, so towards the products here. And adding a neon. No change. Neon's that inert gas because it's one of those noble gases that does not react, so therefore it's not going to affect our equilibrium position. It's just going to add overall pressure to the system. How about decreasing the pressure? Going to shift or proceed towards the reactants because we are going to want to make more moles of gas. And if we increase the volume, we're going to want to. Pressure is going to go down. Increasing the volume means making more moles of gas too. Yeah.
If you increase the number of moles on one side, then you would be an opposite side.
Yes, because that would apply Avogadro's gas law as well. I can see that as a good way of applying it too. I just usually on the pressure questions stick with boils, but yeah, you could look at it that way too. Very good. All right, just a little bit about the Haber process because it's been very important in agriculture. There's this big apparatus here where they're manipulating lots of things through the Le Chatelier's principle. And it's very important that we make these ammonia-based fertilizers because agriculture makes a lot of our food, and if we don't have the food, then we can't feed people, and you know how this goes. So it's a significant part, and it's making sure that we make and use our reactants to the most. And you'll see Le Chatelier's principle being applied here in manufacturing of these fertilizers. So here's the big apparatus. This one's actually in your book, but it shows you like the incoming gas here, incoming, okay? And then they have some come down here and they get heated. They also pass over a catalyst. We'll talk about catalysts in just a minute. And then they go up here through a heat exchanger. And these are hot gases that come over here. Another heat exchanger is going to cool them down to make our ammonia. So there's all these manipulations going on, so you get your liquid ammonia coming out here at the end. And it's being removed as the process is going, so you're going to keep the forward reaction going. We want the forward reaction going because we want to make the ammonia here. All these different, pressures applied through Le Chatelier's principle is going to give us the greatest amount of output of the ammonia. So very cool. And this is showing that the system here, but also if you have your total pressure, they figured out the right pressure in ATM, about 500 ATMs, and your temperature around 400 here is that maximizes the output. The maximum output they get when they manipulate the variables to those particular ones, the pressure and the temperature, is when they get the 60.6%, because you know the percent yield is never going to be 100%. But as you can see, if they have them at different temperatures or different pressures, they're yielding different percentages. But if you were a business person and you had to pay for your reactants, wouldn't you want to maximize and get the most percentage you could for your reactants there? And so by manipulating the system so that you get the most ammonia out each time. So here's a true application of Le Chatelier's principle at work here. Catalysts. Let's talk a little bit about catalysts. We're going to get into that more in kinetics, but catalysts lower the activation energy of both the forward and the reverse reactions. So, does it have any overall effect on our equilibrium position? No, the answer to that is no. That's true. It's not going to affect our equilibrium position. It's going to lower the activation energy in both directions, therefore speeding up both directions equally. As you see on your potential energy graph over here, as you see here, the activation energy is lower, the hill's a little bit lower. But going forward, going backwards, it's still going to now be an equal rate, but it's just going to be a faster rate because the catalyst is going to make it go faster in both directions. Okay, so our end up uncatalyzed is just slower, but you eventually end up at that equilibrium position, still the same. Doesn't change the equilibrium position at all. Okay? So catalyst is a no changer, just like the inert gases, no change. Okay? One uses a catalyst, equilibrium is achieved faster, but the equilibrium composition remains the same. So no change in equilibrium position. Good with that? So no change for catalyst, no change for adding in noble gases or inert gases. Those are going to be those main ones that they like to throw in there as the added little extras. But